Hi, welcome to Norton Engineering University. I'm Chris Steves. Today we're going to be talking about process troubleshooting for refinery engineers, and we'll be going over a case study from an FCC feed system that was experiencing upsets. If you haven't already watched the first part of this series, which talked about the overview and principles of process troubleshooting, I encourage you to watch that and see how these principles are applied in an actual case study from a troubleshooting episode. In this particular feed system, the FCC unit, which is a fluid catalytic cracker unit found in most refineries around the world, the unit had been restarted after a major turnaround. And as it was starting up, about a day after startup, the unit was experiencing major disturbances in the feed, with the pressure and the feed rate was swinging rapidly and out of control, and it was happening about every 4 hours. These swings were causing major upsets in the fractionation section as feed was being rocked around in the feed system and then into the reactor, and then from the reactor into the fractionation section. These swings in feed rate and pressure were also limiting the unit feed rate. The unit was running very close to the trip point on the regen catalyst slide valve differential pressure, and so operators were having to keep the unit at lower rates than normal in order to try and keep the unit from tripping automatically with the shutdown system. Here we have a schematic of the system. This is also a good thing that you should do when you start your troubleshooting, is draw a picture of the system so you can see what it looks like and help you in identifying what the problem may be. In this feed system, the feed is coming from tankage. It's running through a feed pump and then a series of preheat exchangers where it's exchanging heat with products from the fractionation section to heat the feed up. It then goes through a feed furnace, a fired heater. There are 4 passes in this fired heater, and the feed splits to each of the 4 control valves that control the feed rate to each of those passes. Then the feed recombines into a single stream and runs into the FCC reactor. At the feed injector nozzles, there's dispersion steam that's mixed with the feed in order to help with the dispersion of the heavy feed into the catalyst stream so that the FCC reaction can occur. There are pressure gauges on the system so that you can see what the pressure is, and these pressure gauges were the indicators that were telling us that we had major feed upsets. First thing we started doing was started to collect data around the system. So in looking at the system, we realized that the swings, the pressure swings, were most pronounced downstream of the feed heater. There were swings in the feed rate and the feed pressure at the feed pump, but those swings in feed pressure were much more dampened at the feed pump than they were at the downstream pressure gauge, downstream of the feed heater. The operators, and talking with the operators and interviewing them about what they'd seen in the past, they reported that they'd seen similar upsets in the past, and it was usually caused by wet feed. So if there was water in the feed that was coming from tankage, that would then vaporize partially in the feed train and cause these kinds of upsets. Good information to have. The operators at the tank farm were interviewed. They said they were checking for water at the tankage and they weren't seeing any significant water accumulation. Additionally, some additional data was collected, and we did some experimentation to try and figure out what was happening. So we're generating hypotheses and testing those to try and rule things in or out. Samples were taken at the feed pump. They were taken before an upset, during an upset, and after an upset, and there was no water that was identified. Feed and dispersion system control schemes were also placed in manuals to make sure that there were no issues with the control system malfunctioning and causing these issues with variations in flow and pressure. There was no impact from putting those control valves on manual on the disturbances. The dispersion steam, that piping was checked, and it was found actually to contain significant amounts of condensate buildup at the low points. This was later identified to be carryover from the steam drum where the steam was being generated. Those low points were continuously drained to make sure that we try to not have any condensate buildup, thinking that the condensate could actually be causing these upsets. Unfortunately, as we opened the continuous drains on those low points, there was no impact and the upsets continued. Finally, a process engineer was able to figure out what was causing these particular upsets. He walked down the feed system, and he noticed that the steam out piping that was present on each of the feed heater coil system control valves, that was on a dead leg of the steam system, and there was only a single block valve between that steam line and the feed system. So Thinking that that might be a potential cause of this issue, suggestion was made to operators to double block that steam valve and to add some steam traps to try and make sure that we didn't have any condensate that was building up in that leg. Sure enough, the problem was resolved after that steam out piping was double blocked. Here's a schematic of the piping at the preheat train control valve to show you a little bit more detail what was happening. The feed from the preheat train is coming into the control valve for the passes to the heater. It's a typical control valve station. We've got a control valve with block valves and a bypass. And downstream of that control valve, we've got a connection for steam so that we can steam out the piping. This is typically used before going into a shutdown to remove oil from the system as turnaround prep. As the system was found, there was a single block valve that was closed and one block valve that was open. What was happening was that condensate was building up because of the improper operation of the steam drum. Condensate was building up in that steam line up against the fully closed block valve, and when condensate level reached high enough to overcome the pressure differential, it was actually pushing through the closed block valve, which evidently did not have a tight seal. And then that condensate was leaking into the feed piping, which then ran to the feed heater. As the condensate vaporized, it was causing the pressure disturbances and causing the feed rate disturbances. So closing the second block valve solved the problem. So you can see in this example, we used a systematic approach for troubleshooting, collecting data, interviewing impacted parties, and trying out different hypotheses to see if we could find a solution. But the solution to the problem could only be found by getting outside and walking down the system, seeing the layout and the geometry of the piping. Although not the source of the problem, the troubleshooting also identified additional problems that were discovered that should be addressed. Obviously, there's a need to do something about the excessive condensate in the steam system. So additional steam traps were added, and steam drum separation was identified as an issue that needed to be addressed during future turnarounds. Thanks for listening to this presentation and this case study on troubleshooting. If you've got any questions, we'd love to hear from you and see how we can help you. We can help you with process troubleshooting, project development, and other process engineering needs. Thank you.